night here slumbering, something dark inside, craving only flight. I need it right now, won't let it drown. And we've come so far.
Hi everyone, Christopher Paolini here, and it is my great privilege to be interviewing none other than Greg Meholic today. Hi Greg.
Hi Chris.
Now for those who don't know, Greg, you provided some invaluable technical assistance, guidance, instruction when I was working on creating a lot of the technical or science fiction technology for To Sleep in a Sea of Stars. But why don't you tell our viewers a little bit about who you are and what you do and what got you interested in all this stuff in the first place?
Okay. Well, I've always been interested in faster than light travel. I mean, it always has been something of a personal interest of mine ever since I was about maybe 18 or 19. And really started looking into it when I was in college. I went to college for aerospace engineering, but I also had this other unknown passion for physics, but I knew I wasn't capable of doing any of the heavy math, but I've always been interested in things like that, especially faster than light travel and, teleportation, quantum stuff and quantum phenomenon and whatnot, and just started doing my own studies. And then sort of built on those things as I started reading more and learning about things, and learning about different ways of looking at the solutions to problems that already exist, but looking at them in a different viewpoint. To say, hey, the answer might be 10, but 10 what? 10 this or 10 that? And just different alternatives of solutions for certain things. Many years later, after that graduation, obviously, I think. You had contacted me in the 2010, 12, 13 somewhere time frame, and I had been in California for about 11 years, I think, somewhere around that time. And I had already had a couple of papers that I had written on my own pet rock theory of faster than light travel, but it was something that you latched onto. I forget where it was you saw my name or an interview with me at a conference that I had attended on, and the interview was on YouTube. But you had reached out to me and asked if I could explain some things about it, because you were considering this idea of a new book. And I was not familiar with your work. I'm not a science fiction reader because I just never had the time to sit down. But it was really just fascinating to hear the questions you were asking, because it got me thinking about the theory more and more and more. And in order for you to put together a story that made sense from the world you were developing in your book, I had to really go back and think about a lot of the great detailed scenarios you were providing about, like, hey, what if you could do this? Or what would happen if you fire this thing from a superluminal bubble? Or how would you communicate? And I started really, I haven't really thought about that. I've thought about some of the mechanics of maybe one aspect of that, but not all of a real, the dynamics of a universe, where there's all sorts of, causal things, cause and effective things that go on. So that was really, enlightening to hear your questions and to really get me thinking about a lot of things. And so we just kind of kept in touch. And then I know you went off and wrote things, and it had been years since I had heard from you. And I think we just recently, over the past year and a half or even less, since my move to Virginia here, which was 6 months ago last week, started connecting again. And that's when, it coincided with the release and, the wonderful acclaim that the book's been receiving. And, it's just been an absolute honor to keep in touch with you through this, sporadically, but through the process. And it's been really great.
I was looking at my emails, and I think the last email before we reconnected, was, I want to say 2014, 2015
Yeah.
maybe. It was almost 5 years ago or something. And because we'd been bouncing stuff back and forth, and then I just got so deep into the writing and ran into some real difficulties with it. And it was just like me going into a hole and just pulling everything over my head to try to see if there was even a book I could publish. And I figured, I'm sure you had completely written it off at that point, that the book would ever see the light of day. But hey, look, it happened. It happened.
Yes.
It's a big one. It's funny. It's funny you mentioned the questions, that you were stumbling upon when you were looking into FTL, and that was getting you thinking about, sort of the gaps in established knowledge and what if this and that. Because that's actually what led me to your work in the first place. I was doing this research on Faster Than Light, and because of course, this is a very technical conversation, so I'm not going to shy away from the sort of nitty gritty, which I normally do in my regular interviews because I don't want to bore people. But the problem with Faster Than Light is that if you don't have it and you're writing science fiction, your stories are going to take hundreds or thousands of years, and that that causes problems of its own. So
yeah,
but the problem with Faster Than Light, according to established physics, is if you travel faster than light, you automatically have a time machine. Mm-hmm. And that I just kept ramming my head against that, because every time I thought I found a solution for it, the article would end with, and Einstein says this doesn't work. But Einstein says this doesn't work. And Einstein says this doesn't work. And I was ready to throttle Einstein after a while. But I found one of your, I think it was a PowerPoint presentation that ended up on the internet for some conference that you'd done or presentation you'd done. And it outlined sort of the ideas you had for, slower than light, the luminal realm and the superluminal realm, and how they all interacted. And specifically the fact that in that theory that you were outlining there, you could travel faster than light without traveling through time, at least not backwards, at least not backwards through time.
Right.
And I was like, I need to know more, because it was explained, but I had other questions.
And, that was that was the thing too. When I would hear about it, or from people that taught advanced physics, some of my professors, or I would read about it in book, I would run into those same things. Einstein said this isn't possible, or if you travel faster than light, you have to go back in time, or whatever. And there were things like light cones and Lorentz transformation and stress energy tensors and all sorts of complicated math with no numbers that I just did not have and still don't have the ability to comprehend in my own head. And the way I think about that is that there's nothing wrong with those incarnations of how we have been able to model that level of nature from what we understand. Math is our tool. That's the way we use the tool to represent what we assume or presume will happen in nature. But since I'm not an adept user of that tool, I had to think of some other way, and that I could explain faster than light travel that didn't require or didn't counter any of the mainstream, well-established, modern physics, special relativity, general relativity. And I came across a book in the library at my college when I was about 18 and a half, maybe 19. So I was in my freshman year, maybe early sophomore year. And it was this tiny little thin paper book from the Rand Corporation by a guy named Edward Pusher. And it was about faster than light particles called tachyons. And it was part 1 of 2, this book. And I don't know if it wasn't really a book. It was like a final report. It was like on a project. And it was from 1980, and it was all Arial font, and hand-drawn graphs, because that's all they had back then, no color. But this guy took the equations of general and special relativity completely algebraically and said, hey, if you graph this, here's what it looks like: X and Y, energy and velocity, and you have these 4 quadrants of curves, and we are in this quadrant up here with positive energy and positive velocity. But within that one quadrant, you have 3 different curves. One curve represents kind of what I like to call the subluminal realm, which is everything like us. Mm-hmm. And then there's this luminal asymptote, where you can never approach the speed of light no matter how much energy you put in, which we know to be true. And then there was this other bizarre curve on the other side that was much larger and took up a lot more space. And it was where you cannot slow down to the faster to light speed. Everything has to be going faster. And it's backwards. No matter how much energy you put in, you could never slow down to the speed of light. And the more energy you take out, the faster you go, with some infinite speed that's asymptotic, depending on how much. So I was just completely baffled.
Give our viewers an idea of what putting energy in or taking energy out might actually be. Might actually be in like a physical sense, a practical example.
Sure, you accelerate in your car, right? You push the gas pedal down, more energy from the gasoline gets converted to thermal energy, which pushes the pistons and your wheels turn and away you go. Right now, imagine pushing on the brake and that happening, right? And, I'm sure there's been some cars there's a recall on that, right? But, you push the brake and you go faster. You step on the gas and you slow down. Refrigerators heat things up. Stoves cool things down. That's the kind of reversal of energy that is envisioned to happen in this other realm, right? But interestingly enough, as I kept reading this paper, it basically said, through just the basic algebra, real mass can exist over in that space, in superluminal space, mass like you and I and the planets and stars. Time goes forward. There's no backwards time because you are traveling in a world or in a realm of the universe where traveling faster than the speed of light is a must. So there's no jumping over a barrier like most people envision what faster than light would be, where you turn on, you get to 99% the speed of light and then you turn on the big thruster and you jump right over. It doesn't happen that way.
And the mass that's faster than the superluminal mass never crosses the light speed barrier, and the subluminal mass never crosses the light speed barrier because they're both correct in their own realms. That's right.
And so, and what that did is, as I mentioned, I'm not a very good user of the tools, but I was reading a lot of the math, but I was reading things about dark matter and dark energy at the time and a variety of other things. And that was one of the first connections I made or at least supposed connections. Well, wait a minute. If real mass can exist in superluminal space, and this curve shows that it can exist at energy levels that we can't see, what if dark matter is really mass that exists in superluminal space? And it's a much larger energy realm to take advantage of than what we see in subluminal space. And then I started thinking about it even more about, how certain things move away in gravitational. So I ended up bringing a theory of gravity that was made by this whole thing. And this is called the tri-space, the tri-space nature of the universe. One of the earlier papers I had submitted about this got kicked back from the reviewer, who was a physicist, and I know the name very well. And he'd said, well, this violates all sorts of conservation laws. You can't just take one thing out of subluminal space and make it go faster than light because you're violating conservation and all this other stuff. But when you consider that the superluminal realm is actually part of the entire, it's 1/3 of the universe. There's the subluminal, the luminal, and the superluminal. That is the whole universe. So there's no conservation violation at all. You're just changing form from one to another. And similarly, your mass and energy switch back, where energy existed, mass now does. And then when you switch, mass gets replaced, or energy gets replaced with that mass in the different space. So anyway, like I said, it made it a little bit easier for me to understand, because I could put things completely into graphical terms into my head and see how that would happen.
From a science fiction world building standpoint, which is how I was approaching it, the fact that the superluminal realm, the way it works is that the slowest speed you can go is the speed of light, and there's really essentially no top speed, although that is limited by perhaps the lowest energy state any particle or wave form could reach. But because of that, it meant that the top speed of the universe, the speed of information, was much higher than the speed of light, which instantly raised the cap of how fast spaceships could move if they could access that realm, or any signals, what have you. And that instantly solved so many of the issues I was having from a world building standpoint.
Yeah, and that's actually and that part of the theory had was one of the earlier couple of offshoots that came out of building this tri-space thing, is that, hey, and you hit on it exactly about, if if the information can travel that much faster, then what we in the subluminal realm see as instantaneous phenomenon, like quantum tunneling, may actually have an extremely fast upper speed limit. You know, it may be occurring at some superluminal finite speed, but it just happens to be so fast we see it as instantaneous because we're just not used to seeing speeds like that. And plus all the information and all that we collect through all the detectors we have are all based on the fundamental laws of the subluminal and luminal realm, not the superluminal realm. So, you know, just the instrumentation that we're using to collect data from these types of experiments is already biased, and naturally so, right, by being in our particular area of the universe, in our realm. But yeah, so that does open up some really interesting prospects about, well, maybe the quantum existence and quantum phenomena do occur more inside of this superluminal realm. And that has actually gotten a lot of traction over the years as this theory's gotten built up more and more, even since our first couple of emails. You know, the notion of the more than just the realm of space times, but what is it? What are they made of? And it turns out there's like this fluidic nature, right? Which I think was introduced at the time when you were starting to write your book. And I started thinking about that more and more too, because it just made sense. And being the aerospace engineer, where we got, you know, heavy duty educations in fluids and thermodynamics, it just seemed that overall nature, no matter what scale, quantum level or cosmological, all looks like the same set of physical laws. And there might be physicists going, oh, hell no, the quantum physics laws are, you won't see that kind of stuff in quantum tunneling and galaxies and all, you know, but when you think about like the structures and how things work and the dynamics of things, it all looks very much the same. And there's a lot of analogs and similarities that you can you know, impose on these things to make them easier to understand at both the subluminal realm, the luminal realm, and the superluminal realm, all being what I'm now calling basically different phases of the same stuff. Interestingly enough, like we might be in the liquid form, you know. Then there's this luminal plane, which is sort of this fuzzy stuff called two-phase flow in fluids, and then there's the gaseous form, which is superluminal. The superluminal realm, you know, so there's all sorts of very interesting analogs to think about that for that like, universal structure.
It's like if you take a long enough point of view, things that often seem completely solid to us, like granite or mountains or things like that, will behave like a liquid over long enough periods of time. You know, if you had a time lapse of the mountains of over billions of years, you'd see them flowing and moving almost like water.
Exactly.
You have to have the right point of view in order to appreciate that.
Absolutely.
So how would you go about? Actually two things. So one, you know, when I was writing To Sleep in a Sea of Stars, because it took so long, I was living in mortal fear over those years that somewhere someone would find some discovery on dark matter or dark energy that would immediately disprove every possible thing I was writing about, which is a lesser concern than perhaps you might have for these ideas. But because To Sleep in a Sea of Stars is set in the real world, albeit a couple hundred years in the future, it's the same desire you had, but from a fictional one side of things, where I didn't want to contradict physics as we know it, because it still has to exist in my fictional universe. But all that said, so how might we humans go about proving some of this in a practical sense, at least to figure out, is this real or is this not?
Yeah, that's a great question. And that's one that I get asked, you know, because this is a very speculative, hypothetical theory, right? And so they always says, well, how do you test it, right? You know, because one of the other downsides of that I get, and one of the other weaknesses I get from reviewers that review any of the technical papers, is that I don't have enough math in the papers, right? They said, you need more math. You need some math to show your ideas. And my response to that is, well, I'm not trying to show any new math. I'm trying to show a different way of looking at the answers that already exist, right? And so, you know, yeah, that selfishly absolves me from having to come up with any new math, because I just couldn't. You know, I don't have an army of grad students to go figure that out either. But that's not the whole point of the model, right? The point of the model is to show a different way of looking at the solutions. But to kind of get to what you were saying about, you know, having these certain discoveries or observations maybe counter some of the things that are already existing. I haven't run into that yet, which has been strangely interesting. There was just some articles that came out recently over the past couple of weeks about, hey, dark matter might actually be this weird fifth dimension mass from, I think fermions or something like that.
I saw that.
I was like, see? And I have countless other articles like that sort of, where it's more, credible people than I that have the requisite backgrounds, because I am certainly not an advanced physicist or an astrophysicist, any of that stuff. But they're starting to see that there might be these unusual fluidic type of things, or maybe this hyperspace or alternate dimension, which is, again, kind of the science fiction-y terms. But to me, that's the superluminal realm. It all still seems to fit. I haven't had to make any dramatic changes to the theory to go, oh crap, that was a wrong idea, because what we know now, everything still fits, in the 20 years or more that this theory's been in place. It just keeps getting more supported.
One of the things that I really appreciated about the theory is when looking at different science fiction franchises and sort of the scientific explanations for how the technology works. I mean, sometimes it just is pure fantasy, like the Warhammer 40,000 franchise, where it's essentially fantasy in the future. And then even like Star Trek, there's a few gestures toward science at times, but a lot of times things work at the speed of plot. They work because they need to. And of course, that is true. That is true of my own story. I don't want to say I'm perfect in that regard either, but working with a theory that had been worked out so well and sort of dealt with a lot of the things that are open questions at the moment, as a writer, gave me just this sense of solidity in the universe as I was writing it. Because, especially setting things a few hundred years in the future, you have to assume we're going to learn more, we're going to discover more, we'll be sending probes out, we'll be running experiments that are unthinkable at the moment. And I just couldn't believe that in 300 years we won't have, or 250 years, that we won't have a much deeper understanding of the universe. And I was able to do things in the writing and with the story and with the mechanics of the story that I could not have done if I'd just been inventing it all whole cloth.
Wow. Well, that's really great to hear. Yeah. And now I remember the question you asked, is you asked about like what could we do to test this, right? And then I started on the tangent about the whole math thing. But I think there are opportunities for us to begin to look at the possibility of fluidic space, because that's kind of key in this whole thing. Mm-hmm. If we can show that space-time, and it doesn't matter, it doesn't have to be in deep interstellar space, it doesn't have to be in some multi-billion-dollar collider and buried under Europe somewhere. We can do this in a lab, because it has to be done in some place that can be readily accessed in any part of the universe, or any part of the world rather. With all the current conditions of atmosphere and things like that, because space-time's still there, right? No matter what is flowing around us, it's still there. So we should be able to be able to isolate, or try to detect what the heck it is, because we really don't know. There's quantum foam, which talks about, what is that? There's a lot of theories about that, about how there's quantum fluctuations and particles coming in and out of this foam, but what really is that? Then there's string theory, and
I was going to ask you to rant on string theory for a minute, because I looked into it. I looked into it as one of the explanations, and I found it incredibly unsatisfying.
Yeah, for those that know what it is, it probably is very satisfying, right? It gives those folks something to think about. But honestly, it is so into the details of physics that I that's one of the, if I can't get back past a simple like transformation matrix, I'm like, yeah, that's too complicated for me, So to try to talk about string theory is just like way out there. But again, that's a tool. That's a representation model of something, right? Or at least what could be something, everything's made out of these little strings. You tie it in a bow tie, you get an electron, you tie it in a double Windsor like a tie, and you get a proton. Who knows, right? But it's some kind of, and they wave and things like that. But to me, that just seems too complicated. There's a more simplistic elegance to nature than that, I think.
was kind of my instinct as well. It's so complicated, and so many of the various versions of string theory postulate all of these extra dimensions.
Yeah.
And I mean, I love an alternate dimension story as much as the next science fiction fan, but when you're postulating, 10, 20, 60 extra dimensions or more, it makes me twitchy, because I start saying, well, where are these dimensions? It should be something that we can detect, or that has some influence on the universe around us. And of course, it would be argued the influence we see are, actual physics as we know it. But
Yes.
I don't know, saying that there's all these hidden realms, the universe has always been what we can see and what we can interact with. And even with the tri-space theory, the idea that there's the superluminal realm that perhaps we're not directly interacting with, but there's still very tangible physical evidence of it in terms of the gravitational interaction from one side to the next, from the superluminal to the subluminal. But yeah, string theory gets so far off into the weeds there. I mean, I'm sure the math is convincing, as you say, but
Yeah.
it makes me twitchy.
Well, one of the other things to kind of go back on the thread that you just started there about, something tangible, right? And the tri-space is basically, there's 3 dimensions, right? I mean, not length, width, height, but subluminal, superluminal, and luminal, right? And that's it. But what was really interesting was back in 2007 when I heard about the work of Richard Gautier, and I think he's mentioned in the book at some point.
He is.
Because Richard's work, he's a physicist at Santa Rosa State College in California, and he's published numerous papers on these things. But he came up with a model of the electron and the photon that both incorporate a very, very strong superluminal characteristic that's inherent in them already. And he's been able to I don't know if I want to say solve, but he's been able to replicate the results of experiments and the observations of these particles that we know very well with his model, as well as address others that have not been able to be captured, some other characteristics that haven't been able to be captured by current models, like the jittery motion of the electron. There's no real good model for that, but Richard's model addresses that, as long as the electron has a superluminal characteristic to it. And so once I read about this, it really struck a nerve with me, in that if that's really true, then every particle has a superluminal, a tie to the superluminal realm already within us right now, you and me, right? And so what prohibits us from crossing those 2 dimensions, or crossing that, those 2 realms? If it's already inherent in matter and in mass, even at the electron and photon level, how can that be exploited for things like moving a starship over there, or moving anything over there, right? To try to get that to work.
You've mentioned a couple of times, the fluidic nature of space-time, which is something, of course, I incorporated into sleep also. But do you feel like with that's simply an attempt to replicate the ether, that we're going back?
Totally.
I love how you don't even avoid it.
I'm not going to shy away from that at all. No, because from what I understand, and this, again, I'm not a physics historian by any means, but the ether was one of those accepted things, right? I mean, even the Greeks knew it, because they knew, hey, if sound has to travel through a medium, light must also, right? And so they came up with this concept of the ether, that light has to travel through something, right? And then, of course, that, lasted for a long, long time. And then the quantum realm came along. Heisenberg and Dirac and Pauli and those folks all started to think about the quantum nature of things. And the quantum models started to be able to answer things that the ether models couldn't really address, because they were sort of too global. They were too large scale, at the ether level. But the quantum dealt with the very small, and uncertainties and probabilities and things that the ether didn't deal with, because the ether was more concrete, right? And so the ether got abandoned in favor of this whole new desire to interact with this quantum model, right? And try to replicate things like, things of nature using quantum mechanics. But there were other things that quantum mechanics couldn't explain that the ether could, and so, but it still just got pushed off to the side and said, yeah, quantum is the new thing. Then we had quantum electrodynamics, quantum proton dynamics, and a variety of other, different things that have come about. But I think the ether is, that's sort of the ancient term of fluidic space, which is the new sexy term, right? And so when you talk about fluidic space in terms of a homogeneous medium that is able to transport things like photons and electromagnetic waves, it becomes, as I said, all the way back to fluidic space, or I should say all the way back to fluid dynamics, where everything is the same. All this, the laws are basically the same no matter what scale. Space-time is everywhere. It's the same space-time between galaxies as it is between an electron and a proton. So it's just different phases of the same stuff.
Well, I found it pretty interesting when I don't know if this really ties in, but when I was reading about there was a physicist somewhere who said something along the lines of, I know, it was a discussion about the Big Bang and what may or may not have existed before the Big Bang, right? And the concept of nothingness was being discussed. And this guy made the point that we have never seen or experienced nothingness. And people, when you say like, when you say nothingness or the emptiness or something, people might think of the vacuum of space, right? Except we now know that that's the quantum foam, that there are there's basically a seething inferno of energy on a very tiny scale, and little virtual particles popping in and out of existence. And so he was saying we don't even know if nothingness can even exist. We don't even know if nothingness is a real thing. It may be that there has always been something and always will be. It's almost like it's such a high level question. It passes beyond physics and enters, philosophy.
Yeah, that becomes the medical physical realm, right? Metaphysical, where it's like, how does consciousness warp space and things like that? Yeah, so I've known a few people that have looked at that sort of topic as well, but I'm more more tangible than those things, maybe.
More on the practical side of things.
Yeah, right. How much oil does it take, and when do you change the plugs, that kind of thing. So, yeah.
Yeah.
But it's
so one of the consequences I thought was cool. One of the consequences of assuming that space-time is fluidic, as in the tri-space theory, is it provides a pretty good explanation, I think, for, as you mentioned, gravity, but also like inertia, because if space-time's a fluid, then that means you get resistance if you're trying to move through the fluid, and you can get basically low pressure environments behind a moving object, and so forth and so on, right?
Exactly. Yeah, that was the second it was, I think, the second or third paper that I ever wrote and published in 2002 was on the tri-space theory of gravity and inertia. And again, no math, right? There's not. I don't think there is an equation in that paper other than to say, here's where the tri-space theory initially came from, right? To kind of more of an introduction. But it's all, if like you said, if you have this fluidic analogy or assumption that space-time is a fluid, there are a number of analogies that you can put forth that we know from our everyday world that clearly can describe or model the assumption that gravity and inertia are based in a fluidic type of interaction. They are not caused by electromagnetic fields. They cannot be manipulated by electromagnetic fields. And it is, gravity is a resultant effect of mass, and all sorts of very interesting things. But the analogies, as you mentioned, like low pressure systems behind something moving, and that space-time and has a, the medium of space-time has a time lag. Absolutely, we're back into the fluid descriptions now, viscosity, and to go back into our prior conversation about, what experiments can be done. If there's a way that we could measure the viscosity of space-time, the time lag between when something moves and when space-time has some sort of detectable reaction to it, that would be pretty huge. To show that, yes, space-time is kind of like a fluid. It has the same types of qualities that we know about fluids we can apply. Compressibility, viscosity, density, and energy we already do. Pressure we already do to some degree. But we could really start applying those things and figuring out, what the characteristics of space-time really are. What are the fundamental constituents, which space-time also, or tri-space also surmises based on Richard's work. And what are the phases of space-time? That's something fairly new. like gas liquid type of phases of space-time. And each phase is a different realm of existence type of thing. So it's really interesting how this is all coming together based on fluid dynamics.
Well, and one of the consequences, as I recall, is that if it were possible to transition from the subluminal to the superluminal realm via manipulation of the space-time fabric, warping it, as that's not even the right word, but, actually basically dumping energy into the luminal realm to distort it in different ways. The consequence of that is basically artificial gravity. You would also be able to manipulate inertia by increase or decreasing the viscoelasticity, the viscosity of the space-time continuum.
Exactly. No, that's exactly right. That is one way to create artificial gravity or create a signature, right? To mirror something that would be, that actually would be gravity. It just wouldn't be caused by a mass. So it's real gravity. It's not artificial. It's artificially created because it's not being created by mass. So yeah, there's different ways of looking at that. Mm-hmm. One interesting little anecdote about, you mentioned the Big Bang and what, somebody you had met talked about the Big Bang and what had happened before. But here's an interesting story, and this happened last year. Back in the days when I was actually going into my office, I would have to get up early for work, and my wife liked to have her tea in the morning. So I would take a cup of a coffee cup, and I'd put water in it from the sink. I'd put it in the microwave. 2 minutes later, after it's already feverishly boiling in the microwave, I'd take the cup out of the microwave and put it on the counter. It would stop boiling, right? Because it's cooling down naturally. Mm-hmm. But then as soon as I would put the tea bag in it, it would vigorously boil again. Okay, so interesting, right? This thing is it is sitting on the verge of changing phase, but it is all liquid at that point. And then some little perturbation comes along and all hell breaks loose and you get this chaotic phase change. Mm-hmm. So what if the Big Bang was exactly that same phenomenon? There was some homogeneous form of space-time that was on the verge of changing phase, and then something comes along and changes it, and we now exist in a bubble of superluminal space, right? Or subluminal space, right? And it obviously permeated out, right? And it's cooling, right? It's expanding and it's cooling at the same time, right? Anyway, just something weird occurred.
I guess the question, of course, is what that perturbation would have been, whether it was some random quantum event or some outside force, or it always goes back to the question of what caused the cause.
Yes, right. There's only so far back you can go, right? But yeah, it is really. But again, we're back to the fluid dynamic nature of things. We're back to three phases. Solid, liquid, gas, or somewhere in between. Things of fluidic, like I said, it just seems to me that that's the simplistic nature of things. And we choose and we see and we use the tools of math to try to describe these things. And obviously they become very complicated when we try to do that. But in a sense, it all comes back to some simplistic common set of laws that seems to obey it in any scale. Mm-hmm. And may someday allow superluminal travel to happen.
So where do you see physics? I was going to say science, but I'll confine it to physics. Where do you see physics going in the next, let's say, generation or so? And how do you feel about humanity's chances of colonizing the solar system at the moment?
Let's see. Where do I see physics going? I mean, like I said, I'm not really a physicist to really follow those sorts of things because there's so many different branches of physics. Mm-hmm. But I would say, talking about the topics that we've covered here, I would really like to hope that there is some better identification of what space-time is, because I think that's kind of the key to everything. Mm-hmm. What is it? I mean, because everything exists in it, and this is another thing that has always bugged me, is no matter what theory I read about what is the source of an electric field, what is the source of a magnetic field, what really is going on. People talk about electric fields and charge, and these fundamental characteristics of particles, like charge is a big one, right? Something either has a positive charge or a negative charge or no charge. But what is it? What is it that gives it that property? What's physically going on? And the only way to do that is to assume that there is some medium that is transmitting this characteristic that we identify as charge, right? That's what we call it. But I haven't seen a good theory to explain that. And what I would hope that would come out of the next generation is something that looks at the fundamental constituents of what we would call space-time, because I think that's going to answer so many questions. What are the fields? What's gravity and inertia? What's dark matter? All that sort of stuff will all come out of that one finding or that one approach. As for humans colonizing the solar system, eventually, yes. But I think that what often gets overlooked, and it's sort of it's the pragmatic but pessimistic view, is that the amount of technology and the amount of energy that it takes to do that from a single planet is extraordinary. I mean, look at this, the Space Launch System, right? That one singular rocket is going to be $1 billion per launch, or some ridiculous amount of money. And there's some architectures that require 12 or 13 of these things to launch, to put something in space to allow us to go to Mars or further. But I mean, when it comes down to, the unfortunate things like money and politics, it makes that really challenging, and the resources available. So yeah, eventually we're going to get there, but it's going to be, I think it's going to be a longer road ahead than we're hoping, unfortunately. But having been in the space business for 25 years, it just seems like that's the way it's going. Hopefully my son and your relatives will have a better chance of doing that.
Fingers crossed. Are you familiar with like orbital rings, the concept of orbital rings?
Is it one like it's a central colony, like all that's like totally orbiting a star or something?
That would be a ring world. An orbital ring is, as my understanding is, it's a kind of a cool concept where you. So the problem with space elevators, as you know, is of course the tensile strength of the ribbon. The tensile strength that is required for the space elevator ribbon is slightly beyond our reach at the moment, and may beyond the reach of any material in the near future. But an orbital ring could be done even now. So the idea is you launch up a bunch of ferrous material, and you basically make a chain that orbits around whatever part of the planet. It goes completely around the planet, and it's in orbit. And then you build a tube around the chain. And the tube is essentially like what you have with the maglev trains and stuff. So it's a magnetic accelerator, and it is stationary relative to the planet. So what it does is it generates a magnetic field that accelerates the chain going around. And as it rotates, it wants to fly outward. And that actually provides an outward force that holds the shell around it in place. And the cool thing is this can be built at almost any orbital level. You can be close to the planet, you can be all the way out at geostationary or wherever. But because the outer tube around the rotating chain is stationary, you can build it nice and wide. You can build houses on the outside. If you build it close to the planet, gravity will be actually pretty close to what the surface gravity would be. And it's a super, super easy way I say easy, but it's a super low cost way to get stuff up into orbit, because you can run stationary elevators from the ring down to the surface at heights that would actually be reasonable for, steel and other modern construction, modern elements. I don't know. It's something I've been reading about, and it's like it would be a pain in the ass to build, but if humanity could do it, it's the next best thing to a space elevator. It might actually be better.
Maybe. I just.
I can see you doing the math for like how much material would you have to actually launch into orbit, right?
Well, not so much that. I mean, that would come, but the first thing I was thinking of was just that, it would be interesting to know, because this is something I fairly recently learned what is what the dynamics are needed to get something into orbit. Mm-hmm. Right? Like, orbit is more than just altitude, right? I mean, it is speed, and it's a speed that is different than the Earth's rotation. Yeah. So, just the fundamental physics of what an orbit is going to challenge the physics of space elevators and orbital rings.
Yeah.
because there's so many differential velocities, and it's not 5-10 miles an hour. It's 10 to 15,000 miles an hour kind of thing. They're not small changes in velocity. They're very large changes, right? And then there's the energy to affect those changes and get something to orbit, right? So, and the further out you go, the less the velocity is, but the more energy you need to get out there. So it's like this, like I said, it becomes very, we'll just say that's challenging. Right?
Do you think that long-term nuclear rockets are going to be our best bet for space?
Considering I'm working on nuclear fission and fusion, I'd say yes. I mean, I'm going to be biased towards that.
I was going to ask you about that. You mentioned you're working on some sort of fission or fusion drive at the moment, or something like that?
Yes. Yeah. NASA actually has a very active program going on right now on nuclear thermal propulsion. And they're looking at nuclear electric propulsion, mainly for their vision mission to go, send humans and cargo to Mars. They're both being looked at very, very closely. There's active test programs going on. And there's other government agencies that are also very, very interested in looking at nuclear power and propulsion in space for national security missions because of the efficiency that type of propulsion system offers that you just can't get from a chemical system. Mm-hmm. And so, it's sort of the next evolution, at least how I see it, and many others. The next evolution of rocketry is a nuclear system, all in space, right? I don't know if there's anybody that's going to ever allow a nuclear engine to launch from the pad to get to orbit, but you really can't beat chemical for that. That's just, brute force is the best way to go. And we've been doing that for 70 years, and that seems to be the way that we're going to continue to do that. But once you're in space, there's a different set of parameters that drive what your requirements are for a propulsion system. And depending on your mission, which is extremely important, right? And nuclear propulsion is not a one size fits all, save us from everything and, Mars in 60 days kind of thing. But it definitely offers advantages that chemical systems don't. And a lot of people are starting to take notice of that right now. More so than they did, 50, 60 years ago when NERVA was going on. There's a lot more now that we've been able to do to evolve that technology with today's computing power and materials, sciences, modeling, and manufacturing techniques. It's definitely getting a lot of traction.
I think a lot of people don't realize just how far and how fast you can end up going if you have a spaceship that can basically thrust at 1G consistently. That was when I was doing the research for To Sleep. I was doing research into what would be the range, what would be the velocity, and other things you could have. What would be the delta V you would have with a high-end sci-fi fusion drive that could hit 1G of thrust and maintain it for, let's say, days even, right? And it's crazy. It's absolutely crazy. I mean, as I recall, I might have the exact figures wrong, but if you had a spaceship that could do that, you could basically take off from Earth, fly all the way out to Jupiter, turning around, slowing down, and flying back and land on Earth. And you could do the whole thing in I think it was 6 days or 12 days. I mean, it was absolutely bonkers how fast you end up going if you can maintain that thrust. But of course, maintaining that thrust and even achieving it is the challenge.
Yeah, that's actually there are all sorts of wonderful opportunities to think about how these types of propulsion systems, with their efficiency and potential thrust, might be able to do these sorts of things like you described. One of the things that we've done recently is look at fusion propulsion specifically. Since it's definitely up and coming, there's a number of companies that actually have, really good, sound, fundamental, based in physics, real physics concepts for fusion systems that we're looking into. But when you consider the subsystems that have to support that engine, so you might have this fantastic engine, it could give you 100,000 pounds of thrust and this really, really high efficiency. But when you consider the other systems that have to be in place for that engine to function, and that is mass you can't get rid of. That's mass you have to have on board your vehicle, right? And it's mass, it's power, it's all sorts of other requirements start to drive, and they start to build on one another to the point where you got to end up trading fusion with other systems because it doesn't appear to be as clean of a win as it was when you started the study. you know, one example is like, okay, some of these fusion systems run on deuterium, right? That's a very common fusion fuel. You know, it's not maybe the best, but it's a common fusion fuel. But in space, you want to have a small tank, right? Because a tank is material and it's mass, and you want to make it light. So you need to store deuterium as a liquid to keep its density high, right? So you can have a small tank. Well, how do you cool deuterium? Because it's almost like hydrogen. So you have to keep it cold at minus 400 and some degrees below zero. And so that requires additional coolers. Well, what powers those? Where does that electricity come from?
Yeah.
And then how do you get the cold deuterium into the engine that needs gasified deuterium? Where do you heat it up? How do you heat it up? Where do you get that power?
Yeah.
What is going to keep those systems cool? What's going to drive the coolant pumps? What powers the coolant pumps? Again, you start building all these subsystems around, and you end up going, I need all of this just to run that engine.
Yeah.
Right. And it's a little different from like a nuclear fission engine or a chemical rocket engine. But nuclear fusion definitely has challenges, but it also offers a lot of significant benefits, like the significant reduction in radiation, things of that nature.
As Heinlein said, there ain't no such thing as a free lunch.
Right.
You always pay for it somehow. You know, what you were just saying reminds me when the first Iron Man movie came out, Wired magazine had some article on the Iron Man suit, and they were looking at it like, could this be actually built, and could it do the things that we see it doing in the film? And aside from a couple of artistic liberties, their conclusion was everything the suit does could be done right now with today's technology. We would just have to plug the suit into an entire nuclear reactor. Because it's the power that it consumes, it's all the jets and all the various things that it does, and we don't have the energy storage and we don't have the energy production to make that possible in a small package.
That's right. And so that's when you get into things like matter, antimatter, right? But then that's a whole different set of challenges, right? Yeah. I mean, it's not science fiction, but the production rates maybe are, of how to produce enough antimatter, or I should say collect it, right? I mean, it's produced all the time, but, capturing it is a real problem. Mm-hmm. So how do you do that? And if you could do that, then, that would open up a lot of doors, right? How do you capture it and store it and be able to capitalize on it? But that would be the energy source, right? That's the most energetic process in nature.
That actually raised a question. I'm not sure I've ever asked you this before, but have you ever thought with the tri-space theory about the disparity between matter and antimatter?
I have, yeah. Interestingly enough, that goes back to Richard Gauthier's work. He actually was able to put that into perspective based on his models that look at how electrons and positrons and photons all have a superluminal characteristic to them. And it was really, really interesting that he came up with something like that, saying, yeah, this is why we have more than we do of the other kind, or at least, that seems to be more prevalent. So that was really enlightening too. And like I said, some of the work that he's done has been able to address things like that maybe some areas of physics have sort of relegated to other parts of physics. Like, oh, we don't touch that. That's their job. We're over here in quantum physics. We don't worry about the matter-antimatter balance. But it's all the same, right? It's all the same, it comes back to being all the same type of argument and being able to explain things with a similar solution. So yeah, Richard sort of addressed that. And I haven't necessarily needed to incorporate that in the tri-space model. But it is something that I can go to, at least from Richard's point of view, and get more information.
Gotcha. So and I want to sort of try to convey to our viewers just how many questions I did ask you that you were very kind enough to answer. I mean, we're talking some emails that were verging on, I don't want to say novella length, but they were certainly essay length. So if there are any other aspiring authors or actual authors out there who suddenly have a burning desire to ask questions about the tri-space theory, is that something you would be open to doing in the future again?
Oh, absolutely. Yeah, 100%. In fact, after 10-year hiatus, I actually decided to write a technical paper that I'm gonna to try to incorporate some of the newer nuances of tri-space that have come about over that past time. So I'm going to present that at the last American Institute of Aeronautics and Astronautics, otherwise known as AIAA, Propulsion and Energy Forum. They're going to run the last one of those in 2021. I don't know yet if it'll be virtual or real, but then they're going to phase that out and go to another larger conference called Ascend, which they just started last year. But anyway, I wrote a paper, or I'm going to start writing a paper for it. I don't even know if the abstract got accepted yet, but yeah, absolutely, I'm willing to take questions on it for sure.
Well, you'll definitely have to send me the paper when and if it gets written, because I'd love to read it and probably bang my head against it a little bit and see how much I understand.
Yeah. Like I said, if I can understand it, hopefully others can as well. Because I try to keep it super simple for me.
Yeah. Well, and in the back of To Sleep in a Sea of Stars, I have essentially a fake technical sort of white paper that reviews sort of a lot of the concepts of tri-space as it is implemented in my fictional universe. And, as I say in the acknowledgments, the large majority of that was drawn directly from your work, and you were very kind to read it over and provide some extremely helpful edits on that. So a big thank you from me. And I've had a couple of readers write back to me and say, I felt like I was back in high school, college advanced physics again reading this, but well done.
Oh, nice. Okay. Yeah, that's great. Was one of the other person I want to just give credit to that I've collaborated with on this, not just Richard Gauthier, but Dave Froning. Mm-hmm. You mentioned his name in the book also. Dave and I met in the early 1990s because he had a similar kind of model, but he wasn't quite sure about how to interpret it. He had this idea of if you could employ specially conditioned electromagnetic fields that he calls SU2 and SU3 fields, where our current magnetic fields are like SU0 and SU1, but he's talking 2 and 3, that you could actually like rotate out of our dimension into something else that would allow you to do these superluminal speeds, and then he would sort of flop back in and rotate back in to our realm. And he was also an aerodynamicist for many different, mainly Northrop and Martin Marietta and things like that. Mm-hmm. So he had that whole fluid dynamic things too. So when him and I started to collaborate on, hey, maybe you're rotating into this other dimension, a superluminal space. And he went, yeah, maybe this whole rotation thing is this transfer mechanism. So we really collaborated, and back in the mid 2000s and 2010s-ish, we started writing some papers on how do you transform from one side to the next, especially with Gauthier's work and what are some of the other options. And so we have some really good papers on that too.
And that a lot of that provided the basis for that technical section I wrote. That rotation reminds me, my sister had the best description of faster than light travel I ever heard, which I used in the book. She said that traveling faster than light was like traveling. Now I'm going to forget the exact quote. I cannot believe it. It's something like traveling along a right angle, but in a straight line.
Oh, interesting. Yes. That's a really good way. That's a really good way of putting it. Yeah.
Yeah.
And when you're at that scale, there is no curves. It's all straight anyway.
Yeah.
There was one other thing I wanted to mention. So I wanted to say, just to make sure I give a shout out to Dave. He's in Australia. He's been there for, 15 years. I don't know he's always been up in years. So I don't know if he's even still with us. I sure hope he is. Again, this whole thing with the whole tri-space doesn't involve time travel, because I wanted to avoid that. That just didn't make any sense, so. Yeah.
Well, I'll have to talk to you about my time travel ideas, but that's a separate conversation. Sure. Well, thank you so much for taking the time to talk today. This was an absolute pleasure. I quite literally wouldn't have the book I have today if not for your very kind help and influence.
Thank you, Christopher. That's really kind of you to say. Thank you, and thanks for being such a wonderful collaborator on this. To listen to these crazy crackpot ideas and put them into a story that is, absolutely remarkable and getting significant recognition. Thank you. That just really, I'm so proud of you and so happy for you that this has come that you've done this in your career.
Well, thank you. Well, physics and storytelling are almost the same in one way. It's an explanation of how things happen. And
Right.
I've just been very, very lucky to have a collaborator and someone to advise me through this. And I'm really pleased with how it turned out. So, and also I want to give just mention for those who are watching that my team and I have just launched a massive new website for the universe of To Sleep in a Sea of Stars, and it is called, the website is fractalverse.net. And if you're interested, you can go there and find some of the technical information we've been talking about there, as well as tons of cool science fiction art that I commissioned just for the Fractalverse and the book itself. So be sure to check that out. Greg, again, thank you so much for talking, and we'll have to do this again sometime.
Absolutely.